Hello. Today I'm going over 154, and this says to check the divergence theorem over the volume of one octant of a sphere radius r for this vector function v is equal to r squared cosine theta r hat plus r squared cosine phi theta hat minus r squared cosine theta sine phi phi hat. So the first step here is to compute the divergence. So in order to do this, it's spherical coordinates. So you have 1 over r squared partial by partial r squared times the r component. So this becomes r to the fourth cosine theta. So the derivative of r to the fourth is 4r cubed. And then we have to remember we're dividing now by r squared, so it just becomes r cosine theta. And now we're adding 1 over r sine theta partial by partial theta sine theta r squared cosine phi. Derivative of sine is cosine, so now we have cosine theta r squared cosine phi over sine theta r. And now for this one, plus 1 over r sine theta partial by partial phi of minus r squared cosine theta sine phi. I should have a bracket right there. And here it's essentially the same thing, minus r squared cosine theta cosine phi over r sine theta. These cancel, and we're just left with 4r cosine theta. So now the next step is to just integrate this over the volume, and all right, so to compute the integral, we have to take the divergence. We integrate the divergence over the entire volume d tau. And d tau in spherical coordinates is r squared sine theta dr d theta d phi. So we already know that the divergence is equal to 4r cosine theta, and this is the Jacobian dr d theta d phi. Now the limits of integration are a little tricky. For r, we're going 0 to r, big R. And now for the phi and the theta directions, theta is normally 0 to 2 pi. It normally goes the whole circle. And phi is normally 0 to pi. If we go 0 to 2 pi, we're counting the same points twice. So we don't want to do that. So no, 0 to pi is what we normally integrate over, and it's the angle that the z-axis makes. So in order to get an octant, now we have to take a half of that, so pi over 2. And for our theta, for 2 pi, now we want to get a quarter of that, because we just took a half of what we would normally take. So to get to an octant, we take a quarter of that. So now we're at, we take a quarter, and that's an eighth. So 0 to r, 0 to pi over 2, and 0 to pi over 2. And we can also write this as three integrals being multiplied together, because we don't have to solve for we don't have to really have to solve for the limits of integration. We already have them. So we can do 0 to r, big R, 4r cubed, 0 to pi over 2 d phi, and then 0 to pi over 2 sine theta cosine theta d theta. Now the only real interesting one is this integral, which can be done with an easy u substitution. Let u is equal to sine theta, so du is equal to cosine theta d theta. So u is equal to du over cosine theta is equal to d theta. Okay, so now when sine theta is equal to 0, u is equal to 0. And when sine theta is equal to pi over 2, u is equal to 1. So now we have u du. And the reason for that is real simple. Du over cosine theta times cosine theta is just du. And that just gives us u squared over 2 from 0 to 1, which is just 1/2. So this just gives us pi over 2. Pi over 2 times 1/2 times r to the 4th over 4 times 4. Well, that's r to the 4th pi over 4. And that's the result that we want. Now, to check this, we're going to take 4 different surface integrals. So there are 4 surfaces to this octant. We have the entire front, and then there's S2, and then S3 is like on the other side, and then S4 is going to be on the bottom. So to compute the surface integrals, we have to take v dot dA. Now, when we do surface integrals, dA, it's going to be a little tricky. So we have our components r hat, theta hat, phi hat. So for our first component, it's going to be r hat. So surface 1, the front surface, the curved surface, is this r squared cosine theta r hat dotted with dA. dA in this case is going to be the component that's missing. So it's going to be r d theta, r sine theta, d phi. So our r in this case is going to be like a constant. So r squared cosine theta r hat dotted with r squared sine theta d theta d phi r hat. We don't have to worry about the other directions because r hat dot theta hat, for instance, is going to be 0. So now we could just do this 0 to pi over 2, our usual integration. And r in this case, r here is this equal to big R. Little r is big R in this case. So is this becoming a constant? R to the 4th. That doesn't look good. Make it look like an exponent. R to the 4th. Integral 0 to pi over 2 d phi. 0 to pi over 2 cosine theta sine theta d theta. And we've done this integral already. It's r to the 4th pi over 2, and then this is 1/2, so we get r pi over 4 r to the 4th. And that's for the one integral. Now we still have to do 3 more integrals, but it's going to follow the same process. For our second surface integral, dA is in the phi hat direction. So now phi at this point is equal to 0. And we could just do this by r d theta dr. So, and it's also in the like negative direction in a sense. So it's minus r dr d theta. So v dot dA is minus r squared cosine theta sine theta, sine phi. And there is a phi hat right here on this one. Dotted with minus r dr d theta phi hat. So the phi hat is just to show that they're in the same direction. But since phi is equal to 0 in this case, the second one is just going to be 0. So, and I've kept tally of our integrals right here. 0 plus the first surface pi r to the 4th over 4. So this one is a 0. And then when we do the other side, now phi is going to be equal to pi over 2. And now it's r dr d theta. So v dot dA is similar, but not 0. It's going to be minus r cubed cosine theta times sine of phi, which is pi over 2, which is just 1 in this instance, dr d theta. And now we integrate that, 0 to r, and then 0 to pi over 2, r to the cubed minus cosine theta. So we get r to the 4th. And the integral of cosine is sine from pi over 2. So this is 1. That's 4. Minus r to the 4th over 4. And we still have one more to go. For our final surface integral, we want to find, we're going in the theta hat direction with theta is equal to pi over 2. So dA is r sine theta, dr d phi in the theta hat direction. So v dot dA is r squared cosine phi times r sine theta, dr d phi theta hat. So r cubed sine theta cosine phi, dr d phi. Integrate that from 0 to r cubed. This is just going to be equal to 1. So cosine of phi, 0 to pi over 2. And that's going to be r cubed. So r cubed is going to be r to the 4th divided by 4. So 0 to r. So that's r to the 4th over 4. And as we can see from here, r to the 4 and these two cancel. So our answer is pi r to the 4th over 4, which is the same as the volume integral. This was a very interesting problem that basically proves the divergence theorem in a sense. And I just want to thank you all for watching. Have a good one.